You know, in the world of mathematics, some pairings are just legendary. Today, we're diving into what might be the ultimate power couple of calculus, the exponential and logarithmic functions. So, what exactly gives them their unique power? Let's find out.
All right, here's our game plan for today. We're going to start with a quest for truly unstoppable growth. Then we'll meet our two main characters, the exponential and the logarithm. After that, we'll see their perfect mirror image relationship, and finally, we'll uncover their secret calculus superpower.
So, let's kick things off with a big question. We all know about polynomial functions, right? Things like x squared, x cubed. They grow pretty darn fast. The higher you make that power, the steeper the curve gets. But is that the best we can do? Is there something out there that grows even faster than any polynomial you could possibly imagine? To get us thinking, let's set up a little showdown. In one corner, we've got a seriously heavy-duty polynomial, x to the 100th power. And in the other corner, we've got an exponential function, 10 to the power of x. Now, for really, really big values of x, who do you think wins this fight? Well, the results are just staggering. It's not even a competition. When x is 1,000, our polynomial, x to the 100th, gives us 10 to the power of 300. That's a 1 with 300 zeros after it. Absolutely massive. But the exponential, 10 to the x, that becomes 10 to the power of 1,000. It is so much bigger, it's on a completely different planet. This shows that exponential growth is just in another league. And that brings us to our first hero, the function of unstoppable growth, the undisputed champion of speed, the exponential function.
So, what is it, formally? An exponential function is written as y equals b to the power of x. The key thing here, the absolute game changer, is that our variable x is up in the exponent. The base b can be any positive number bigger than 1, so it could be 2 or 10 or, as we'll see in a minute, a very, very special number.
Now, all of these exponential functions kind of share some family traits. You can plug in any real number you want for x, no problem. But the output, it's always going to be a positive number. And here's a cool trick. Because any number raised to the power of 0 is 1, every single one of these functions passes through the exact same point on the graph, 0, 1. From there, they just take off and keep on climbing. Okay, so among all the exponential functions, there is one that's the undisputed star of the show. Meet the natural exponential function, y equals e to the x. This e is a special number, kind of like pi, and it's roughly 2.718. Its unique properties make it unbelievably important in science and, you guessed it, calculus. And you know, every hero needs a partner, right? A counterpart that brings balance. So let's move on and meet the other half of our power couple, the logarithm. The whole reason we need logarithms comes from a really simple question. We know that 10 to the power of 3 equals 1,000. But what if you work backwards? What if you start with 1,000 and you want to figure out what power you need to raise 10 to? How do you actually solve for that exponent? And that is precisely the job of the logarithm. The expression log base b of a equals x is really just a different way of saying b to the power of x equals a. That's it. In short, the logarithm is the function that goes and finds the exponent for you. It's the perfect inverse. Now, check out how the features of the logarithm perfectly mirror the exponentials. Its domain is only positive numbers, but its range is all real numbers, the exact opposite. And just like the exponential has that key point, the logarithm always passes through the point 1, 0. It's also always increasing, just a whole lot more slowly. This whole mirroring thing is absolutely not a coincidence. It creates this really beautiful visual symmetry, which we can see perfectly when we put our two biggest stars side by side, the natural exponential and the natural log.
The connection between e to the x and the natural log of x isn't just some clever math trick. When you actually look at them on a graph, you see that they are perfect, beautiful reflections of each other.
Let's just lay it all out. The exponential passes through 0, 1. The log passes through 1, 0. The domain of one becomes the range of the other, and the range of one becomes the domain of the other. See the swap? This is the classic signature of inverse functions, and it means that geometrically, they are perfect mirror images across that diagonal line y equals x. It's often put just like this, and it's perfect. The two curves are the mirror images of each other, reflected in the line y equals x.
This beautiful symmetry isn't just nice to look at. It's the visual proof of their deep inverse connection. It's form and function in perfect harmony.
So, okay, they have this really elegant relationship, but what makes them a true power couple? Well, their real strength, their superpower, only gets revealed when we bring them into the world of calculus.
In calculus, we are obsessed with the rate of change of things. We find it using something called a derivative. And when we ask for the derivative of our two functions, something truly remarkable happens. And here it is. The derivative of the natural log of x is a really nice clean function, 1 over x. Simple enough. But the derivative of e to the x, it's e to the x. It doesn't change at all.
Let that sink in for just a second. The natural exponential function, e to the x, has a property that no other function has. Its rate of change at any point is equal to its value at that point. To put it another way, its slope is equal to its height. This is its unique superpower, and it's what makes it the fundamental building block for modeling all kinds of continuous growth and change.
So what are the big takeaways here? First, exponential functions model the fastest kind of growth imaginable. Second, logarithmic functions are their essential inverse partners, built specifically to solve for the exponent. And finally, the star of the show, e to the x, is its own derivative, a unique superpower that makes it absolutely indispensable in calculus.
So now that you've been properly introduced to this mathematical power couple, the real question is, where will you see their patterns in the world around you? From compound interest in a savings account to the growth of a population, their influence is literally everywhere. What are you going to see differently now?